Good evening, everyone, or good morning, or wherever you are. I'm Stuart Feeser, and this panel are going to join me in studying all the things that I wish I knew before I built my first cloud. In fact, these things that I want to share with you tonight are things that I wish at the end of a week's worth of teaching, it would immediately become clear. So let's start out with growth is a good thing. Growth means we have to expand whatever we have. So let's assume from the beginning that this is the problem we're trying to solve. How do I deal with growth? That's expectation of what the customer wants versus there's more customers and I have to ramp up. So ramping up means scaling. And scaling means scaling up or scaling out. So we're going to take a look at what the difference is between those two first. If I'm going to scale the hardware, there's four things you think about in scaling the hardware. The CPU core count. So maybe I'm going to install chips that have 20 cores and later rip them out and install 32 cores. Maybe RAM is going to go from 256 gig per compute node. And now I want to install 1 terabyte per compute node. Maybe I want to go from 4 terabytes of storage to 20 terabytes of storage. And I'm sorry, but 10 gigabits is just too slow. We need to ramp that up to 100 gigabits per second per compute node. And while we're at it, let's drop 2 100 gigabit per second connections and tie that up. That's 200 gigabits per second up into the top of rack. Pretty cool, huh? That's all possible right now. That's scaling up. Now, scaling out means, hey, I like what I already have. Let's just build more of it. Let's rack up more servers. Which one makes sense? I wasn't sure I actually knew the answer to that question until I actually put this presentation together. Now I'm convinced I don't know the answer to that question, but at least I know the questions. So first things first, the hardware knowledge that every dev should possess. All of us should know this. So pardon the eye chart, but we got to get through this. On the far left, these are the compute cores. This might be one CPU, and this CPU has a total of 32 cores in it. On the far right is RAM. We all know what that is. DDR4, or the 3200 SDRAMs, move data in and out at an, I'm going to say an arbitrary 225.6 gigabytes per second. I was shocked at how little that number was. For some reason, I expected more. I shouldn't have, but...
Is that random or just...
Yeah, that's random. Yep, whether I'm going to here or whether I'm going down to there. And that's the beauty of it, is that when I hit the system bus, I can go to whatever I want, and that's a huge advantage. Now, remember, we're talking about RAM, not L1 cache, right? Because the name of the game is to guess. It's actually a proven mechanism to say, I think this particular RAM right here, that content, I'm going to copy through the system bus, place it right here in this L1 cache, where this core, 97% of the time, could have knocked me over with a feather. Wasn't expecting it to be that good, that everything I need is going to be right there in the L1 cache, and I'm hammering away at that at a 0.5 terabyte a second. That's cool. Now, as we go out, I see L2 cache, where I have 8 megs of that. That's 8 megabytes, and then 32 megabytes, and this is shared cache among all the cores. The name of the game, particularly for compilers, things that actually produce executable code, they need to write code that it fits in that space, or you're not going to get the performance. Now, that little box is interesting. Let's hold off on that a minute, because this is a well-kept since 1980 secret that the moment I learned that back in 1988, I still don't understand why we don't know what that is, right? So let's go this path. Let's go through PCI. So we know what that is, right? That's the little connection you see like right here. That, by the way, a PCI bus. I'm sure you've seen them on a motherboard. There's one right there. That's a 16, and that 16 number that you see there is the amount of lanes, simply counting the amount of pairs of cables that connect to it. So a little 4X, which can deliver 4 gigabytes per second on PCI 3, compared to, well, let's go up to PCI 4, 16X, that's delivering almost 32 gigabytes per second. I put the arrow there because that's the sweet spot. I think that's kind of where you want to be, and I'm going to prove it. Now, I noticed that all these cores have non-uniform access, which is actually balanced fairly well, I must admit, onto the PCIe bus. Now, I want you to look closely at what directly connects to like the mega speed bus. Just look closely. Uh-oh. Oh no. What's this? You don't want that anymore. This is too slow. You don't want it. So let's look at NVMe, and what the heck is that? Well, it turns out that all that non-volatile memory express is an SSD that's actually packaged normally the way you see them, although they could be in a lot of form factors. They come in a little package that looks like this. Tiny little package, and you're not going to be able to see it, even though that's a 4K camera right there. But if I plug this in, and if you follow the little pins coming out of this M2 package of an NVMe, you'll see the little pins coming down to the PCI bus on a one-for-one basis. And you will not see that kind of configuration on a SATA connection. It's not going to happen there. Slow motion. And it's not the SSD's fault. It's the way it connects to the bus, something every dev should know. So that means if I plug an NVMe directly into the right bus, I can expect to draw 3.5 gigabytes per second per NVMe. Now, let's take a look at the NIC. If I look at the NICs, I'm seeing, okay, I can buy a 100 gigabit bit, not byte, 100 gigabit per second NIC. In fact, normally they come with 2 interfaces on them. That means 200 gigabit per second team. Turns out that's going to draw 25 gigabytes per second. And look at that. This wouldn't work, would it? It's simple math. Something every dev should know. When you're deploying systems, if you cannot outmuscle the hardware if the hardware is not going to deliver. So having the right hardware in the first place is super important. Now, the 10 gigabit per second NIC that we're using in Alta3, don't ever expect to move any more than 1.25 gigabytes per second across it, but that's healthy. And in the training world, that's probably sufficient. But a lot of work could be done right here to improve the performance of our systems. Now let's continue and start to look at some cool things we can do with this. Item number 1 is that direct memory access. It's been around a long time. I'm not sure why it's so secret. The chip is hardly secret, but look what can happen. If we access this NIC the old-fashioned way, I call it the slow way, then we're actually going to drag all the bits that we pull in at 100 gigabits, actually 200 gigabits per second, back through the cores and then dump it into user space. Guys, if you do this, your cores are going to go to like 100% utilization. HTOP just pegs. Don't do that. There's a way better way. If you deploy the direct memory access, as the name implies, then you're going to haul data in off the network, plug it right into user space. That's not root. That's user space. 0 CPU utilization this, other than, of course, to set up the DMA and get it moving, which was trivial. So this is called single root IO virtualization, or SRIOV. It's fantastic. It's based on the Intel Data Plane Development Kit. And the only thing that's interesting about it is this little card next. So let's take a look at that. You can do the same thing with NVMe, because what NVMe really is just an SSD with a PCI interface on it, which means it's designed to hook right into the system bus itself. So when we move data up through here, it's going right into user space. We're burning no cores at all. You want to move data in and out, letting an Ansible playbook thump away at things, then move it in through DPDK. I can't wait to even try to deploy some of this stuff. Seems kind of cool to me. Things that I think every dev should know. But there's even more. This is fascinating to me. Suppose that this is my storage server down here, right? And up here is just a compute node. Now over here are the cores. I want to remind you of that. So what I can do is I can actually pull information off this remote hard drive via DMA, so that's right to the PCI bus, right straight through our 200 gigabit per second network, right? If you choose to run it that fast, and DMA it right into user space. There is about a 5 microsecond difference in latency between hitting the local NVMe versus hitting remote DMA. I mean, how could we not see this coming, right? And it's really cool because, I don't know, it just changes everything, right? Then companies like Weka.io come along, they see all this stuff, and they immediately notice, well, wait a minute, if I'm actually going to drive traffic the old-fashioned way through, let the cores access it through the normal Linux drivers, why don't we just write the drivers to take advantage of all this high-speed stuff? And that's what Weka.io did, and they're having great traction with that. All right, now that we understand how we can scale out the hardware and some cool things that we can do, let's make the software match. Let's make the software take advantage of what's going on. So from the user's perspective, I want to point out that whether we are accessing software written in the monolithic approach or we're accessing software written in the microservice approach, the user doesn't feel any difference. From my perspective, he says, I can't tell the difference between these two applications. Both of these are identical in what they do. Right now, I don't care what they do. My point is that whatever they are doing, it's identical. So which is better? Well, we'll see. I'll let you figure that one out. Just listen. So when you think of monolithic, think of a jigsaw puzzle. It's the pieces interlock, and they only go one way. You can't turn them around or mix them up, and it has to go on a certain table size when you put it together. But microservices, they're Legos. The interfaces, there'll be an API for each one of these, allows them to communicate with each other, and these all don't have to be on the same table. I can sort of spread these around. Let's keep that in mind. So if I'm going to scale out a monolith, remember, that's the jigsaw puzzle approach, and I have 1,000 customers, then maybe the existing servers can handle a small monolith. But if I'm going to scale out a monolith to serve the same one to serve 10,000 customers, remember, think jigsaw puzzle. I need a bigger table to put the puzzle together. That means I need a bigger server. That won't work with the existing servers.
Scale up.
Yep.
Did you mean scale out or scale up?
This is scaling up. The problem with a monolith is you can't scale it out. So yeah, you caught me right there. Thank you. Because the only way I can solve the problem with monolith is up. But it turns out if I can these microservices, so remember, all of these little microservices add up to that monolith that I spoke about. But
you're doing the can.
Yeah, well, you see my can of microservice, and I'm sure all the Kubernetes instructors recognize the YAML right there. So I'm going to can one microservice right there, and I see that I need 2,000. In other words, 2 CPUs, and it looks like a 2 gig of RAM right there. This is in million. This is in thousandths, and this is megabytes is what that is. Well, that's containers, right? But what's never talked about enough is the dependencies. So for once, let me explain what's going on here, at least my vision of it. So here I see app number 1, some cool application that I intend to containerize. And it requires on some libraries. These are things that you would install with apt or yum or pip or maven or whatever you're developing in, right? So it looks like this app is going to need these services right here. And that's always going to need. Oh, and by the way, he is insisting on 3.8 and 1.2. But app number 2, this 3.8 isn't going to work for him. He needs 4.0, and down here he needs 1.5. So having these two apps running on the same operating system is completely incompatible. So let's explore that. Well, one way would be to can up this app. And notice this container that I have here just fits like a glove. I'm not canning up this other stuff, which is crazy because no one ever actually does this. But in my mind, I'm thinking, yeah, this is the way you do it. You containerize only the stuff you need, and you drop it in your app 1 can. It's containerized and ready to go. Ideally, containerizing only the software that supports the app. Let's do app number 2. Oh, by the way, we'll just slide in the 4.0 and the 1.5. Notice that it'll overlay on top of all the stuff that's there right now. We deliver the right goods to this little can of app. And now I have app 1 and app 2 all canned up with all the dependencies in place. Because the idea with the container is that it's not about shipping the app. You know the old saying, it worked fine when it was on my computer. And the answer is fine, then we'll just ship your computer. And what they're really saying is, we're going to ship this. We'll ship the part that you need that makes it work. And now I know it's going to work. And it does work. It works really well. But alas, regrettably, that's not the way we do it. Not at all the way we do it. We take app 2, and not only do we can up the stuff that it needs, we can up all the other stuff that it doesn't need. So when you read the label, it says 3% active ingredients, 97% unused filler, and future security threats.
Build essential.
Yeah, quintessential. Yeah, that's it. So, but that's the way it is. And even so, you can sense this is solving some problems. And even though this is a lot of storage on the hard drive, I mean, who cares? This is going to work. And most of the time, that's the name of the game. But if I have all my little cans, so I have 16 cans of microservices going on right here to serve 1,000 customers, I can scale this out because all I have to do is just duplicate the containers. So I just stack the containers up, and now I'm serving, say, 10,000 customers. This is implying that each one of these probably would have served about 3,500 because I only needed to triple that, and now I can handle 10,000. So scaling then would imply that I would have to, well, actually, this is prior to scaling. I would take my 16 cans, and maybe I put cans 1 through 6 on this server, and I'm just going to do this manually because I'm just crazy, and I'm going to do this right on this one. I just decided to do this, and I immediately forgot where I even put these things, because I know me, and that's exactly what would happen. No matter, and try to keep that on a spreadsheet, that wouldn't even last a day, and I already forgot where everything is. But then you tell me I need to ramp it up. Well, the truth is I can do it with the same server, because if I take all this capacity that I have right here, I need this capacity, and I just say, okay, I need 3 ones, for instance. So I'll run one of them on this server, and one of the cans runs on this one, and one of them runs there. And then you'll see I have 3 2s. And trust me, I painfully went through this and made sure that there were 3 of each on this. Now do that manually. And you're going to realize, I don't want to do this manually. This is crazy. What happens when you come back and you say, oh, I need 6? Or what's worse is, what if you say, I need 6, but at 10 o'clock tonight, the service really drops off, and can you just cut it back to just 1? No, I can't do it, but that's where Kubernetes comes in. I would argue that is why Kubernetes exists. It is like the main thing. So that if I am all scaled out like this, scaled out, not up, Kubernetes is going to keep perfect track of where every one of those cans of containers is running on every single compute node. Kubernetes is going to be aware of the capacity in each one of these compute nodes. And if one of the compute nodes right here is a little fatter and more capable, then the other Kubernetes will reward it by applying more cans of containers to it, right?
And it makes it easy to add a new one too. It makes it easy to add a new one too.
Oh yeah, you just rack them up. You just put a new rack in if you want to, right? And the thing is, if I want to take advantage of all the really cool capabilities that are coming up, like I want to do SRIOV and I want to do all of the really fancy NVMe access through DMA, Kubernetes won't care, because really it's just deploying services, balancing them, I should say deploying containers, balancing them evenly across the entire stack. So Kubernetes actually doesn't take a lot of explanation. I will mention that obviously we're going to have to put software on each one of these. So there's a kubelet that installs on each one of these, and we're going to have to install some master nodes right there. But all of this is covered in our Kubernetes class as to exactly how this happens. But once you lay in all this software, which actually overall wise is a very small overhead, you get all this magic occurring, all this management occurring. So ultimately, where I took you in this, if you really look at it, is this final slide, my final concept here. What we really do in our world is we take data, we process it, and we ultimately produce information. And that's the story that I've just told you, from the hardware perspective all the way up to automation. Okay, that as fast as I could get through there. That was 22 minutes. Sorry for running a little bit past. Questions on that, guys? They're silent.
No questions, actually. Information is what we want at the end of the day.
Yeah, well, what was the most surprising for you? Just curious.
Well, what's cool about what you talked about is you never talked about Kubernetes until the very end, but yet you motivated all the reasons from the beginning.
Yeah.
From first principles.
Right. Yeah. So it's like, how do you even title a talk like this? I don't know how you title a talk like this. Ultimately, you have to be aware of, I believe that containers are by far the best way to deploy a service. And if I have to deploy a service that's going to require more than what I can handle manually, I want something to orchestrate it. And that's what Kubernetes does. Okay, well, guys, let's call it right there then. For all of you out there in YouTube land, thanks for joining. See you next time.